A well-known relation or identity for triangles is that the inverse of the inradius is equal to the sum of the inverse exradii. So here's the incircle of this triangle, this blue triangle P1, P2, P3. It's inscribed in an ellipse. I'll explain this in a minute. But just focus on this particular. In fact, let me turn off the conics and I'm just going to show the triangle with its incircle. So here's a triangle P1, P2, P3. Here's its incircle. It has a radius called the inradius. And here are the three X circles, the externally tangent circles that are external to the triangle, which are simultaneously tangent to the three sides. So they're called X circles, and the radii are known as the exradii. Okay, so these are the radii of the exscribed circles. Okay, so a beautiful relationship or identity is that the inradius is equal to the harmonic mean of the exradii, or equivalently, 1 over the inradius is equal to the sum of 1 over each one of the exradii r sub I. Let's call it that way. So I'm showing this up here, right? Here's the inradius of the system, 0.535. Here's its reciprocal, 1.86. Here's the sum of exradii, which is not germane yet to this discussion. And here's the sum of the reciprocal exradii, which is equal. So you can see that 1 over r is equal to this sum here. Okay. Now, if I embed this triangle in a Poncelet family, let's say, where this triangle is, so this family will be inscribed in a particular conic, in this case is black ellipse, and it's going to be circumscribing a fixed circle, not necessarily concentric with the outer ellipse. So let's look at this Poncelet family here for a moment. So there it is. And you can observe two things about this family, okay? We already know that the perimeter of this family is not constant. The area of this family, of these triangles, is not constant. We know also, and it's not germane here, that, actually no. So we know that the area or the perimeter are not constant, okay? Now what you observe immediately here is that, as expected, because the inradius is fixed, the sum of the inverse exradii is going to be exactly equal to the inradius, which I can place on the screen here. So here's the inradius 0.53, here's the inverse inradius, and here's the sum. Nothing new here, right? Now a miracle happens if you make this caustic be concentric with the outer ellipse. Let's do that. N equals 3. How do I do that? N equals 3 in circle. So if I have a family of Poncelet triangles whose circular caustic is concentric with the outer ellipse, then a miracle happens. First of all, you know that 1 over Ri, the sum, should be identical to 1 over R and constant, but you get a second invariance, which is that the sum of exradii is also constant. And this could have something to do with something that is known about this family, which is that its circumradius, not shown here, is also invariant. So it could be that these two relations are somehow, these two invariances are somehow interrelated. So we get this first thing that we're still analyzing, sum of exradii constant over the family. Okay, so you could ask yourself, okay, what happens now if my caustic is, say, a homothetic ellipse? Do I get anything interesting? It's a concentric homothetic ellipse. Well, here's the incircle. Its inradius is variable. You don't get anything interesting here. Everything is varying. What if this caustic were a, I don't know, confocal conic? Do you get anything interesting? No, you don't. Everything is varying. What if this caustic were a displaced ellipse? So I think I have that here. Here we go. So yeah, so let's just look at this for a second. First of all, I have a triangle P1, P2, P3 inscribed in a conic and a black ellipse, and the caustic now is going to be this tilted non-concentric ellipse. Do I get anything interesting here other than just this interesting dynamic geometry of this Poncelet family? Do I get anything interesting here? No, everything is varying. So no harmonies here. The harmonies occur when either the caustic is a circle. If I can do that. There you go. And what is that first harmony? We expect that. This is nothing new, that the sum of 1 over Ri is equal to the sum of, equal to the inverse of the inradius. This is valid for any triangle. But then you get this surprising harmony, which is when these guys are concentric, you also get that the sum of exradii is constant. Okay, now one of the ideas that we had, and this is the main topic of this video, was to generalize this to the case where n is greater than 3. So let's look at an n equals 4 family, which has a non-concentric circular caustic. So here's an outer ellipse. Here's an inner inner conic, which in this case is a circle. The circle is not, here's the center of the circle, non-concentric with the center of the outer ellipse. And I'm drawing here a Poncelet 1, 2, 3, 4 quadrangle, and I can watch this family over this one-dimensional Poncelet porism, right? Now, a very happy observation is that though this is not a triangle, the sum of the inverse pseudo exradii, what do I mean by a pseudo exradius? I'm actually doing the same kind of construction. I'm actually building 4 circles external to my polygon, which are tangent to one of the original sides, while being simultaneously tangent to the extensions of the incident sides. So you can get these 4 pseudo X circles here, which are sort of similar in spirit to the idea of X circles for a triangle. But one of the observations you make is that if the caustic is a circle, the sum of the inverse X radii is invariant. Let's look at to see if this is the case for n equals 5. So here's n equals 5, non-concentric. Same construction. So I have now a family of 5 gons inscribed in an ellipse whose caustic is a non-concentric circle. You get the same phenomenon. So it looks like this thing is generalizing, and n equals 3 is kind of a manifestation of this bigger thing, right? Now, here's a second observation. Let's now make this caustic be concentric with the outer ellipse. So now I have a family of n equals 5 with a circular concentric caustic. Look at what happens. Both the sum of the inverse x radii and the sum of the x radii themselves are invariant over this family, mirroring what we saw in n equals 3. So that's a very interesting observation. Okay, what else did I want to show? Okay, so now I want to switch gears to the second battery of observations, and this has to do with families that are bicentric. So here's a bicentric n equals 5. What does bicentric mean? It's a Poncelet family inscribed in a black circle while circumscribing a circular caustic. So it's kind of a special case of what we had before, because before our outer conic was an ellipse, and now I'm imposing that this outer conic be a circle. So it's a Poncelet family interscribed between 2 circles. What do we get here? We get the same phenomenon. Even though these 2 conics are not, or these 2 circles are not concentric, you're getting the phenomenon that you were getting before, where you had an outer ellipse and a caustic that was circular and concentric. So you get the phenomenon that both the sum of the x radii and the sum of the inverse x radii is constant. So that's very neat. Does this work for n equals 4 as well? Bicentric. Here's n equals 4 bicentric. Yes, it also works for n equals 4 bicentric. Okay, last observation. Let's do a funky n equals 5 bicentric. Which instead of having turning number equals 1 or a pentagon, I'm going to have a family of pentagrams. And here are the pseudo, so this is a bicentric family of pentagrams, turning number equals 2. There's still 5 gons, and you're still getting this really interesting result, whereby both the sum of the x radii and the sum of the inradii inverses is constant. Now notice one thing I forgot to mention, that the sum of inverse x radii is not equal to the radius of the caustic in none of these cases when n equals greater than 3. So you can see here that though the sum is constant, it is bigger than the radius of the caustic, which is 0.268. Okay, so this is true for the 4 bicentric as well, right, which we saw before. You get invariance on both quantities, but this quantity is much bigger than the radius of the caustic. You get the same result when, for example, here's n equals 5 and the concentric circular caustic. You get invariance, but notice that the second invariance, sum of inverse exradii, is much bigger than the radius of the caustic. The only time when they're actually identical is for the n equals 3 case, right? So in the n equals 3 case, this is valid for any triangle. The inverse in radius is equal to the sum of inverse exradii, and in this case here, you do get that 1.6667 here and 1.6667 there. Okay, so this translates to invariances for n equals n greater than 3, but it does not translate to identicality, or they're not identical quantities, right? So namely, n equals 5, as we saw before, with the concentric caustic. You can see here that the radii of the caustic, which is a circle, is much smaller than that sum. Okay, guys, so this is basically what I wanted to show in this video. Thanks for watching, and I'll see you next time.